Okay, so we're going to go over a couple problems from Chapter 11 homework. This slide is question number 52, and the next slide is question number 72, both from Chapter 11. At first glance, this slide may seem a little bit overwhelming, and in a sense, it really is. It's going to be a review of most of the reactions that we learned in this chapter. And so to simplify things, let's just start where we know, which is the alcohol. If you recall, getting from an alcohol to a ketone is an oxidation reaction. The way they're going to carry out that reaction is through some sort of oxidizing agent. One that comes to mind is H2CrO4. A second one that comes to mind is PCC, pyridinium chlorochromate. And so both of these reagents will pull off a conversion from an alcohol to a ketone. If you go back to that part of the chapter, you can see that we can also take a primary alcohol into an aldehyde. We can either stop it there or we can keep it going all the way to the carboxylic acid. Secondary alcohols turn into ketones, as shown here. Tertiary alcohols do not undergo oxidation. Now the next step from the alcohol is activating that alcohol into a better leaving group, which is this OTOS group. We're going to carry out that reaction using the reagent sulfonate chloride. It's abbreviated as tosyl chloride. We're going to react secondary alcohol with this tosyl chloride in the presence of pyridine to give us the sulfonate ester, which is shown here. And that tosyl group on the alcohol is going to make it a much better leaving group. So in a sense, this reaction right here is activating the alcohol. This is an SN2 reaction. Now if we go back to the alcohol here and we take it to the alkyl halide, that reaction is also an SN2 reaction. And that reaction can be carried out very simply with HBr or with phosphorus tribromide. Both of these reagents separately would provide the opportunity for that alcohol to be activated to leave. In the top case, it gets protonated and water leaves. In the bottom case, we actually activate the alcohol with this group right here, which becomes a better leaving group. And in both cases, it's an SN2 reaction and we get the alkyl halide. Continuing on with reactions of the alcohol, let's take the alcohol to the alkene. So we're going to do dehydration or elimination. And there's a couple different ways that we can do that. The first way and the simplest way is just with the use of acid, H2SO4. That's going to activate the alcohol. Again, protonate, have water leave. That's through an E1 mechanism. The problem with this reaction is that heat and acid or very harsh conditions are required to pull this off. In addition, because it's an E1, we end up getting carbocation rearrangements. And so there's another way to do it, which we have a little bit more control over, and we have better conditions, less harsh conditions. Phosphorus oxychloride, or POCl3. This is an E2 mechanism. This activates our alcohol in a better way, so we have a very good leaving group. There's no chances of carbocation rearrangements, and the conditions of this reaction are much more mild. In both cases, we get the alkene as our product. Yes, because this is a little bit confusing, I'm going to be jumping around, and so if we take our attention now over to the activated alcohol here, this OTOS group, ready to leave, so that's a very activated leaving group. In order to convert this OTOS into our ether, it's a very simple reaction. It's an SN2 reaction where we have to add a good nucleophile, which will be methoxide anion. So in an SN2 type reaction, this set of reagents, when added to the OTOS, activated alcohol, will easily convert to the ether, shown here. Alkyl halide, shown in this step, we need the same reagents. It's an SN2 type reaction, and it's right here. So we'll need this good nucleophile in both cases for the substitution reaction of either the alkyl halide shown here or the OTOS activated alcohol shown here. Now, when we're trying to convert the alkyl halide to an alkene, this goes back to chapter 10. We'll use a strong base in the presence of DMSO to give us the elimination reaction, the E2 elimination reaction, bringing us to our alkene. Now that we have the alkene, there's several different things that we can do to the alkene. We can go directly to the cis diol through the oxidation reaction of osmium tetraoxide in the presence of H2O2 and water. So peroxide and water. This is going to give us our cis diol. That step is an oxidation. Now, if we're going to take our alkene and convert it to an epoxide, we have to show two different ways that we can pull that off. The first way that we learned earlier in the course is through the peroxy acid. And if you recall the structure of the peroxy acid, it looks like this. Remember, we have that oxygen-oxygen bond, which is very unstable. And so this oxygen-oxygen bond in our peroxy acid affords us this epoxide as a product. The second way that we're going to pull that off is through the use of hydrohalogenation. So remember, we have halogens and water in the same reaction. Recall the intermediate from that reaction looks like this, okay? Cl adds to 1, and then we have an O minus. In the second step of that reaction, we have an intramolecular SN2 reaction where this does backside attack there, kicks out the chlorine, giving us our epoxide. That's a hydrohalogenation reaction, which ends in an intermolecular SN2, giving us the epoxide. Now, in order to take that epoxide and give us our trans diols, which are the two products here, we need to simply add OH minus, followed by treatment with acid, which will protonate. I hope you see that this was a nice review of the reactions that we learned in Chapter 11. Certainly not every reaction, but it really does summarize a lot of what we did learn and review. The next question is a little more straightforward. The question simply asks us, propose a mechanism for this reaction here. And because we see that we end up with a ring, we kind of can think this must be an intramolecular reaction. And so, in the presence of acid, I hope that we can start recognizing that the acid is going to protonate one of the alcohols. And so we show the mechanism this way. Remember, please, in order to get credit for any mechanism question on any exam, you have to show all of the arrows for the electron movement as well as all intermediates. So the intermediate that would form from this arrow that we've drawn here from this first step in the reaction looks like this. So one of the lone pairs on the oxygen has now formed a sigma bond with one of the H's. We still have two lone pairs on the oxygen here, and we have a positive charge on the oxygen. The conjugate base that exists after that first step is HSO4 minus. So moving forward, the next step, because this alcohol is activated now and is a good leaving group, we actually have a good nucleophile on the other side of the molecule. So the two electrons from this alcohol come around and do backside attack on that carbon right there, kicking out the water, giving us an intramolecular SN2 reaction. The intermediate looks like this. Of course, we have water as a product. Now in the last step, we can imagine the conjugate base here reaches out and pulls off that proton, and then the electrons that were in that bond hop onto the oxygen, giving us our final product, which is this 5-membered ring with an oxygen and water, and then of course regenerating our acid catalyst. So this mechanism seems pretty straightforward. I hope that you followed my reasoning in both questions, and I hope that this helps you move forward to understand and grasp the concepts in Chapter 11. See ya!